In this video, we are going to learn how to make solutions by adding water to dilute it in a very quantitative way. And so it would be like taking frozen orange juice from concentrate and creating something drinkable by adding water. We are also going to discuss ways that we can separate out solutes from their solutions. So once again, we're going to be using another equation and yet another equation to solve solution-dilution problems. And the equation can be found in your reference table. So if we have an example down here in the right-hand corner, you see a stock solution, and it could be anything, 1 molar, so 1 mole per liter of solution. And if we wanted to make a 0.1 molar solution, we would just take 1 milliliter of stock solution and add 9 milliliters of D water, which is distilled water. And that would be 1/10 or 0.1 molar solution. So we're going to be using this equation, M1 times V1, equals M2 times V2. So M1 times V1, that's the stock solution, both in molarity and in volume. And then M2 times V2, 2 is the final or the dilute solution in both molarity and volume. So let's practice an example. So suppose you have a stock solution of 16 molar nitric acid, and you want to make a dilution of 500 milliliters of a 1.5 molar solution. So you want to really dilute it so you can work with it. 16 molar is toxic. How much stock solution would you need? So we would start off M1 times V1 equals M2 times V2, and you can write down the given. So M1, that's the molarity of the stock solution, which is 16 molar, and we don't know how much of that we're going to need to make a 1.5 molar. We only want 500 milliliters. So we'll just rearrange to solve for V1, excuse me, by dividing both sides by M1. So it's going to be V1 equals M2 times V2 divided by M1. And so that equals 1.5 molar. You do not need to convert to liters in these problems. 16 molar. So I'm just going to plug that in. And it's 1.5 times 500 equals divided by 16. So 46.V1 equals 46.9 milliliters. And so what that means, what that would look like, is I would need to take a beaker. Okay, I would add 46 milliliters of 16 molar nitric acid. And I would add water, add distilled water, until the line reached 500 milliliters, and then I would have a 1.5 molar solution. In the second problem, if we add 250 milliliters of a 0.75 molar sodium hydroxide solution until the final volume is 600 milliliters, what is the molarity of the diluted solution? So again, we're going to say M1 times V1 equals M2 times V2. And then what's given is M1 is 70.75 molar. V1 is 250 milliliters. M2 is question mark. We don't know what the concentration is going to be, but we do know that we're going to make a 600 milliliter solution. So again, we're going to just plug in, rearrange to solve for M2 in this case, and so we're going to divide both sides by V2. So M2 equals, and I just switch this around, divided by V2, so that equals 0.75 molar times 250 milliliters divided by 600 milliliters. And so that solution that we made, 0.75 times 250 equals divided by 600 equals, that's a point, M2 equals 0.31 molar solution, so 0.31. And that makes sense because, because it should be more dilute, less concentrated, considering the volume has considerably gone up. So would we consider dissolving solutes and solvents a physical or chemical process? If we can separate out the solute from the solvent and it still retains the chemical identity of the individual components, then it would be a physical process. And indeed, we can actually separate out the solutes from the solvent. Different ways may include heating or evaporating the solution. Water is much less dense, so it is going to evaporate or boil off, and it leaves the heavier solutes behind. An example can be seen in Death Valley, California, where there are huge salt flats where the very, very dry air has evaporated and the salts are left behind. It's a really beautiful place. A second type of separation technique is called fractional distillation, and it's used to separate out different products of crude oil just by heating crude oil and separating them out at different boiling points. So the lightest, least dense, least viscous, least dense gas, actually, you're going to have very volatile small molecules that boil off first, and so those can be separated out first. And then as you go down this column, you see that the molecules get larger, have higher boiling points, and are separated out at various boiling points. So most of the products, petroleum products that we use are made, plastics, diesel fuel, lubricants, by way of fractional distillation. A third technique that is used in the field of biochemistry, for example, would be called chromatography. Chromo means color. It often is used to separate out colors in materials, and those colors might separate out because they have a difference in polarities. So if you use a polar solvent, the solutes that are the most polar might travel the farthest, for example, or it might be a size-based issue where larger things travel at a different speed than smaller things. Smaller things might travel a lot faster and go farther. In class today, I'd like for you to grab a felt pen and show me your chromatography technique in separating out the colors that are in the felt pen, so you can see me about that.